Hello everyone, my name is Xiang. I'm a postdoc at Harvard University. Today I'm going to present our work on relational analysis of sensor attacks on cyber-physical systems. This is a joint work with Nathan Fulton from MIT IBM Watson AI Lab and my supervisor, Professor Stephen Chong. Cyber-physical systems interact with the physical environment through sensors and actuators. Compromised sensors can lead to system failures. Imagine an autonomous vehicle moving in one dimension that needs to stop before hitting an obstacle. The vehicle uses sensor devices to read the distance towards the obstacle and its velocity. The vehicle can either accelerate or brake. The decision is based on sensed velocity and the distance. In a safe operation, the vehicle may accelerate first and then notice the obstacle and choose to brake in order to avoid a collision. However, when the sensors are compromised, the vehicle may no longer be safe. The vehicle essentially becomes blind and may keep accelerating and in the end hit the obstacle. Basically, sensor attacks can lead to catastrophes. Many sample physical systems are safety critical. Testing-based approaches are insufficient to guarantee their safety and security. We believe formal method is needed. It is important for system designers to understand whether a compromised sensor can cause undesired behaviors, such as violating a safety property or corrupting a critical state. Understanding the impact of compromised sensors requires us to reason about relational properties, that is, the relationship between executions of the original system and the executions of the system where some of the sensors have been compromised. Based on these beliefs, we contribute a formal framework to model and analyze sensor attacks on cyber-physical systems. We first introduced how to formally model sensing and a threat model. We introduced two relational properties that express security guarantees in the presence of sensor attacks. Then we introduced an equivalence relation to reason with the two relational properties. Two sound and tractable proof techniques are developed for proving this equivalence relation. We validate the approach through 3 case studies. Now let's see some details. We work within the formalism of hybrid programs, which are designed to model cyber-physical systems. Hybrid programs can express continuous evolution as well as discrete transitions. This slide presents the syntax of hybrid programs. Variables are real-valued and can be deterministically assigned with a real-value term. A variable can also be non-deterministic assigned, which gives an arbitrary value to the variable. This program structure expresses the continuous evolution of variables. Given the current value of a variable x, the system follows the differential equation for some non-deterministic chosen amount of duration, so long as the formula 5 holds for all of that duration. Hybrid programs also include the operations of clean algebra with tests including testing whether a formula holds at the current state, sequential composition, non-deterministic choice between two programs, and the non-deterministic repetition of a program. Hybrid programs often have this general form, which models a system as the unbounded repetitions of controller actions followed by an update to the physical environment. Here, a program control models atomic actions of the controller and plant models evolution of the physical environment. Paired with hybrid program is a dynamic logic called differential dynamic logic. This slide shows the syntax of these formulas. In addition to the standard logic connectives of first-order logic, differential dynamic logic includes primitive propositions that allows comparison of real-value terms and program necessity, which holds in a state if formula 5 holds after any possible execution of program alpha. Program existence is its doer. We are often interested in partial correctness formula of this form. Intuitively, it can be viewed as a Horo triple. If the precondition 5 holds, then postcondition psi holds after any possible execution of program alpha. Let's go back to the example. This slide shows our vehicle example modeled with hybrid program and the differential dynamic logic. Variable d represents the vehicle's distance to the obstacle. Variable v represents the vehicle's velocity, and lowercase a is the acceleration. Program control models the vehicle's controller. The controller chooses non-deterministically between braking at the rate of b and acceleration at the rate of uppercase A. Variable t models the time passed since the controller was last invoked. The controller can accelerate only if condition psi is true, which captures that the vehicle can accelerate for the next epsilon time units, only if doing so would still allow it to brake in time to avoid the obstacle. Epsilon represents the maximal control interval. Program plant describes how the physics evolve over time control interval. Distance changes according to velocity, velocity changes according to acceleration, and the time passes as a constant rate. The differential equations involve only within the time interval t if t is less and equal than epsilon, and the velocity is non-negative. The design safety property of this model is that the vehicle never collides with the obstacle. In particular, if the vehicle starts with a distance that is enough for it to brake, then after any possible execution of the program control plant, the distance to the obstacle should be positive. Now let's see how we model sensing. Hybrid programs typically conflate the values of variables in the physical model and the sensed variables. For example, our previous model contains a single continuous variable v that represents the value measured by a sensor. To analyze sensor attacks, we separate physical variables from controllers' representation of these variables. That is, we explicitly model the sensed values. Here, we introduce a revised model of our example that separates sensor values from physical values. In particular, we have a variable dp that models the physical distance to the obstacle, and a variable ds that represents the sensed distance which the controller uses. Similarly for physical velocity and the sensed velocity. The program plant is modified to indicate that these physical variables evolve according to laws of physics. As for the controller logic is the same, but we add the constraint that Vs equals Vp and Ds equals dp, which basically says the sensors are working correctly. The controller only uses sensor values, so variable ds and Vs are used in formula psi. When it comes to safety property, it usually concerns what happens in the physical world. So the precondition, the postcondition often refer to physical variables. Here, Vp and dp are used. From this model, we can derive additional models that allow sensor values to differ from physical values, which allows us to model compromised sensors. In our threat model, we allow attackers to arbitrarily change sensor values. Sensor attacks are modeled as non-deterministic assignments to variables that represent sensor values. For example, if velocity sensor is compromised, the constraint Vs equals Vp is removed, and allow Vs to take arbitrary values with a non-deterministic assignment. Up to this point, we have shown how to formally model sensing and sensor attacks. Let's discuss what kind of properties we design from a system that may suffer sensor attacks. Basically, we consume two relational properties of robustness in the presence of sensor attacks. The first property is robust safety. Intuitively, a system is robustly safe if compromised sensors do not affect whether the system is safe. Note that robust safety does not require the attacked system is safe. Instead, it requires that if the original system is safe, then the attacked system is also safe. This difference is important. It allows us to separate the task of reasoning about safety from the task of reasoning about sensor attacks. Another property we consume is robustness of high integrity state. Intuitively, it means that compromised low integrity sensors should not be able to affect the high integrity state of the system. Please find more details about the two relational properties in the paper. To reason with the relational property, we introduce an equivalence relation called H-Equivalence. For two programs P1 and P2, which are repetitions of program alpha and beta respectively, P1 and P2 are H-equivalent if, for any executions of P1, there exists an execution of P2 such that the states of two executions agrees on set H initially and at the end of every control loop iteration. Here, two states are H-equivalent if they have the same values for variables in set H. This definition is symmetric. By choosing the right set of H, we can use H-equivalence to reason with the two relational properties previously introduced. We developed two proof techniques for proving H-equivalence. One of the technique adapts the self-composition technique from the literature on secure information flow. Self-composition often works for deterministic programs by composing two copies of the same program into a single composition, allowing us to reason with relational properties as a safety property. One advantage of self-composition is that we can reuse existing theorem provers for hybrid programs to prove the robustness properties. However, designing the self-composition for hybrid programs is challenging. Specifically, one challenge is the structure of non-deterministic choices, which allows a program to choose non-deterministically between different paths. Sometimes we need to be able to reason about executions of two programs that take the same path. The second challenge is the program structure for continuous evolution choose its duration non-deterministically. Please refer to the paper to see how we handle these challenges, as well as another proof technique we developed for proving H-equivalence. To summarize, we introduced a framework for modeling and analyzing sensor attacks of cyber-physical systems. That's all for the talk. Please find more information in our paper, and we are happy to chat offline. Thank you.